This video introduces you to some word problems that involve acceleration. Before you watch this video, please try your hand at doing the 4 review problems in the Seek-Hay 12 textbook section 2.4. Remember that we're talking about acceleration in a straight line. We'll deal with directional changes later. So when an object is going in a straight line, the simplest formula that we can use is acceleration is a change in speed over a change in time, or if we put that into our magic equation triangle, speed will go on top, time will go in the boxes on the bottom, and acceleration will go in the other box. Now, given any two variables, we can pull the third one out and solve for it. But the 4 review problems are all solved using the same formula. Acceleration is a change in speed over time. So review problem number 1. The velocity of a car increases from 2 meters per second to 16 meters per second in a time period of 3.5 seconds. What is the average acceleration? Well, acceleration is a change in velocity over time. Now you have to recognize that delta means that you actually have to do a little math to get the numerator. So a better way to write that formula would be to spread it out like this, where VF means final velocity and VI means initial or starting velocity. This is something that sometimes students have a little bit of trouble with because they always want to put the biggest number in the VF spot. VF is not the biggest number, it's the last number. So it's not the 2, it's the 16 in this case, because the final velocity of the car is 16 meters per second. Obviously the time is 3.5 seconds, that's pretty easy, but make sure you get that VF correct. It's 16 meters per second. By the way, I did add this 0.0 to the review problem just so there won't be any confusion about how many significant figures to use in the answer. So 16 meters per second minus 2 meters per second divided by 3.5. 16 minus 2 is 14 meters per second divided by 3.5 seconds. Don't forget your units. You should write those down as you do the problem because your calculator will not keep up with the units. You have to keep up with them by hand. Your answer magnitude is 4.0 and the units are meters divided by seconds. Another way to show that is to say meters per second with a dot between the 2 seconds, or to say meters per second squared. Mathematically, all of those ways are equivalent. Now, one thing to make a very big note on is that when you do this calculation in your calculator, 14 divided by 3.5, your calculator will only say 4, but the answer is 4.0. There has to be 2 significant figures in this problem because the number of significant figures in the least good measurement is 2 significant figures. Your answer has to be as good as that. Your calculator will only say 4. You have to supply the 0.0. Review problem number 2. If an automobile slows down from 26 meters per second to 18 meters per second in a period of 4 seconds, what was the average acceleration? The formula is the same as last time. It's a change in velocity or speed over time. You just have to be very careful to substitute in the correct values. I'm not showing it here, but what I always do is I make a list of each variable before I write my equation out. So I would have noted that velocity final is 18, not 26. It's not the bigger number. The final velocity is 18 meters per second. Subtract 26, you're going to get a negative value, but that's okay. 18 minus 26 is 8, but it's negative 8. Divided by 4 will give us a negative 2 meters per second per second. That negative indicates that it is slowing down. We call it a negative acceleration. You could also write that as negative 2.0 meters per second squared. Again, if you do the math in your calculator, it will not give you that 0.0. You have to supply that extra significant figure because your brain, has to know the significant figure rules. Review problems 3 and 4 are very similar to the first two, so without as much explanation, if a runner increases his velocity from 0 to 20 meters per second in 2 seconds, what was his average acceleration? Since acceleration is our unknown variable, the formula is the same as before. The process is the same as before. The final velocity is 20 meters per second minus 0 over 2 seconds. It's 20 over 2 is 10 meters per second per second. Now in this case, our significant figure is a little bit iffy. You could just put a decimal there, like I did on the screen. But in order to show that 0 is significant, a better way would be to convert this particular answer into scientific notation. So 1.0 times 10 to the first power would be a better way to show two significant figures for the answer in this problem. And the fourth review problem, which you were supposed to try before watching this video, if a runner decreases his velocity from 20 meters per second to 10 meters per second in 2 seconds, what was his average acceleration? Even though he's slowing down, we call it acceleration. It'll just be a negative value. We are calculating acceleration, so we'll use the same version of the formula. 2 seconds is our time, 10 meters per second is our final velocity, 20 was where we started. That gives us a negative 10 magnitude over 2, which is negative 5 meters per second, or negative 5 meters per second squared. Now let me show you a few more problems just to introduce a couple more twists on how to do acceleration problems. In 3 seconds, a car moving in a straight line increases its speed from 50 kilometers per hour to 65 kilometers per hour. Meanwhile, a truck goes from rest, which means 0, to 15 kilometers per hour in a straight line. Which undergoes greater acceleration? What is the acceleration of each vehicle? Why don't you pause the video and do the calculation before watching the solution? If you calculated the answers, you'll find that both the car and the truck accelerate at 5 kilometers per hour per second. The point is that many students confuse going fast with a high acceleration. Acceleration is not how fast you're going, it's how fast your speed is changing. So if they both change 15 kilometers per hour in 3 seconds, they both have the same acceleration, even though they are going 2 different speeds. Now let's try our hand at a little bit more complicated problem. NASA wants to send a rocket to Mars. Let's say that their best rocket can accelerate 12 meters per second, and that it maintains this constant acceleration for 16 minutes. How fast is the rocket going at the end of this time? In order to get to Mars, the rocket has to escape Earth's velocity. So it has to reach what's called an escape velocity of 11.19 kilometers per second. Is this rocket going fast enough to make it to Mars? Let's find out. If we are going to calculate how fast a rocket is going at the end of the time period, then what we want to calculate is the final velocity. But our magic equation triangle doesn't have a VF in it. That's hidden in the change in velocity. But let's pull that out. Let's pull out the delta V. And if you take that out of the magic equation triangle, what's left is an A beside T, so we'll say acceleration times time. Now we can recall that a change in velocity is going to be VF minus VI. That'll be a little bit easier now to calculate, except for one thing. Our acceleration has time units of seconds. Our time has units of minutes. We need to get all the units to be the same. So in this case, if you take that t, minutes, it should be pretty easy to convert that into seconds. 16 minutes times 60 seconds equals 960 seconds. So let's use that in this equation rather than 16 minutes. You have to write those units down, folks, and keep up with them so that you can see problems like this when you run into them. So a change in velocity would be 12 meters per second times 960 seconds. You'll see how I rewrote the units for acceleration there so that now you can see the seconds from the time and the seconds in the bottom of the denominator of the acceleration are going to cancel each other out, leaving us with just meters per second, which is an appropriate unit for speed. The 12 times the 960 will give us 11,520. The units will be meters per second. But that's a change in velocity. What we want is a final velocity. So let's write down what delta V means. Delta V is final velocity minus initial velocity. And if you substitute that in, recognizing that the initial velocity of a rocket when it's sitting on the launch pad is 0, essentially you can just mark it out and say delta V and delta VF, not delta VF, but VF. Those are the same thing. So if delta V equals 11,520 meters per second, then VF, final velocity, equals 11,520 meters per second. Now that tells us how fast the rocket is going, but it still doesn't tell us if it can reach Mars. Has it reached escape velocity, which is 11.19 kilometers per second? Again, we're going to run into a problem with our units. Our answer was given in meters per second, but what we want to compare it to is kilometers per second. So we have to do what's called a conversion. We have to find a unit that will, or a fraction that will convert from meters to kilometers. So that's pretty easy. 1 kilometer is 1,000 meters. Just make sure to put the meters in the denominator of that fraction. Now the meters on top and bottom are going to cancel each other and leave us with units of kilometers over seconds, which is what we want. The 11,520 is divided by 1,000 in the denominator, so that's 11.52 kilometers per second. That means that the rocket has indeed exceeded Earth's escape velocity and can break away from the Earth's gravity. So yes, indeed, it is rocket science, and the rocket can make it to Mars. Hooray! To solve that last problem took a little bit of equation manipulation. And one of the things I wanted to show you is that you can manipulate the equations up front and derive equations that might be useful for other problems. So for example, we noted that delta V is VF minus VI. So we could have written our equation like this. So anytime we want to solve for final velocity, if given a constant acceleration, the acceleration can't be changing, we can calculate our final velocity using this equation. Velocity final equals velocity initial plus acceleration times time. An advantage of this equation is that it does not involve any sort of distances. It only involves a constant acceleration. So you can calculate how fast something is going at any given time using this version of the equation. If you take into account that velocity final and velocity initial are both calculated using distance divided by time, then you can further manipulate this equation and derive other equations, such as this one. If you want to calculate how far something has gone, given a constant acceleration, then you can calculate it by using this equation, which doesn't take into account the final velocity. You don't need to know that. You just need to know how fast it started. And quite often, it will start at 0, so that first part of the equation will actually drop out. So for example, in something called free fall, which is one of our next topics, free fall means that you drop something. The VI will be 0, and so how far does the object fall in a given amount of time? You just use 1/2 AT squared. Another equation that sometimes is useful that doesn't involve time is you can solve for one of the variables in this equation. 2AD equals VF squared minus VI squared. Now, I'm not going to make you do any of those problems right now. I just wanted to show you that by combining equations and manipulating the variables, we can derive other useful equations that can be used in particular situations. For now, I'm not going to require you to do any more problems, but instead what I'd like for you to do is to watch a little review video just to wrap up and make sure you understand speed, velocity, and average acceleration before we move on into more complicated topics. So bye-bye for now.